This is the second recording about multiple linear regression. This time you are doing an example. In our example, we have the data about 32 cars. The variables we are interested in are the dependent variable x1. This is fuel consumption. The data are coming from United States, therefore it is measured in miles per gallon. The information about each car that we have and that we can use to predict fuel consumption are x2. This is weight in pounds, or rather in thousands of pounds. We have also x3, the number of cylinders, in the engine, and x4, the number of carburetors. Carburetor po polsku gaźnik. Okay. We want to predict fuel consumption based off the data we have available, which means these four variables. We can start with doing pairwise regressions and look what happens. So, for example, if we take into account the dependence between fuel consumption and number of cylinders, it is the following thing. There is a negative dependence, so the more number of cylinders, the less miles per gallon we can drive, which thinking in terms of European descriptions of the problem, it means that the bigger number of cylinders, the more gas is used. However, if our data is expressed in miles per gallon, then this is decreasing. We can even write down what is the regression function. So in this case, x1, when calculated with respect to number of cylinders is x3, so it will be 1 3, reads 37.88 minus 2.87 times x3. So you can see that with every additional cylinder, the number of miles we can drive using 1 gallon of gas decreases by almost 3. And the strength of this dependence expressed in R coefficient is 0.73. Then we can take the other variable, which is weight of the car, Here again there is a dependence, as we could expect. It is also negative. The heaviest the car, the shortest the drive on 1 gallon of gas. And there is the following formula: 37.20. Sorry, I should probably start with what I'm writing down. So this is the regression with dependent variable x1 and independent variable x2. And the formula says that this is 37.28, again minus 4.34 times x2, and the strength of this dependence is a serious one again. 1, 2 is 0.75. Okay, so now the question is, if we use both these variables, x2 and x3, can we radically rise this number? I mean, can we increase the strength of dependence, which is equivalent to increasing the quality of our prediction? So for that, we use our formulae and we calculate the coefficients. What we get is the regression with dependent variable x1, independent variables x2 and x3. The formula is the following: 39.69 minus 3.19 x2 minus 1.5 x3, and r, this time r squared with independent variable 1 and dependent variables 2 and 3. This r squared reads 0.83. So it is better than the previous cases, 0.73, 0.75, but not radically. Which means that there is probably some dependence between variables x2 and x3. So there is not like completely new, so adding new variable, for example, starting from this regression and adding new variable, say x3, does not add really completely new information, because some of this information could be already contained in x2. As you can see, there are serious differences between values of coefficients. If we, for example, concentrate first on the regression between two variables only, and we want to make an interpretation of this particular coefficient, then we would say that every 1,000 pounds of the weight of the car results in reducing the mileage that can be covered on 1 gallon of gas by 5.34. So let us write this down. With every 1,000 pounds more in weight of a car, the mileage covered with 1 gallon of gas reduces by 5.34 miles. However, if we then look at multiple regression and again ask of the coefficient, not here, with x2, look at the coefficient in front of x2, which is weight variable, we see that the number is completely different. So again, it is the difference between mileages of two cars that have weight that differs by 1,000 pounds, but assuming they have the same number of cylinders. Here, in this example, we didn't take into account the number of cylinders. Here we did. So this is the average difference between two cars with the same number of cylinders and weight changing by 1 pound, by 1,000 pounds. So the interpretation of this is different. So let us write down this interpretation. For two cars with the same number of cylinders, the difference between distance covered on 1 gallon of gas is probably the average distance between average difference between distance covered on 1 gallon of gas is 3.19. But there is this difference for two cars with the same number of cylinders. There is a problem here because it isn't written anywhere that this is really for the same number of cylinders with the same number of cylinders. We can also look at the plot of our regression function, which is everything now happens in 3 dimensions. Probably it isn't that well visible as in case of 2 variables. When there is a clear picture, there is a regression line, there is a scatter point plot of the data points. Here we have the same, but without the possibility of looking from different sides on this picture, we cannot really gain any information. For that, I advise you to use the Mathematica notebook, which is available on campus. You can look at the picture from different points of view. Okay, so let us try to explain why the increase from 0.73 or 0.75 to 0.83 is not that big. This is because when we look at the regression, the linear dependence between a number of cylinders and weight of the car, there is a clear positive dependence with r squared between 2 and 3 variable being equal to 0.61, which is quite an impressive dependence, which means that some of the information that our additional variable, this time x3, puts into the picture is already contained in the previous regression with less number of variables. To see it clearly, we can use the following formula. If we want to calculate r squared for the multiple regression using variable x1 as dependent and 2 and 3 as independent variables, provided we know all the pairwise coefficients, we can write it in the following way. So we can take r12 plus squared plus r13 squared minus 2 r12 r13 r23 and divided by 1 minus r23 squared. We will derive this formula in a moment, but let us first explain what's what. So here we have the measures of the strength of linear dependence between pairs of variables, so square of the Pearson correlation coefficients. And here we have just Pearson correlation coefficients, not squared. So this small r, say ik, it is the covariance of xi, xk divided by standard deviation xi, standard deviation xk. So r squared ik, it is small r ik squared. So what we can see, for example, if our two independent variables are completely independent from each other, so if this is 0 and this is 0, then this cancels and this cancels, and then really our coefficient here is composed of two parts. So this is the information coming from one variable, this is the information coming from the second variable, and we add them. However, if there is non-trivial relation between variables 2 and 3, then this thing is quite complicated. It is complicated because this dependence appears not only here in the numerator, but also in the denominator. To see that this dependence is not really that easy, let us look at the multiple regression between x1 as a function of x2, x4. So this is again weight, and this is this time number of carburetors. So here we have pictures. First regression is the same what we had already seen. So this is x1 with relation to weight. and this is, maybe we can make it a little bit bigger. This is x1 with dependence of x4, which is number of carburetors, and there is the relation between x2 and x4. So number of carburetors with respect to weight. And you see that the dependence here is much smaller than previously. In particular, in terms of the squared correlation coefficient, we have here r squared to 4 equal to 0.18. And r to 4 is positive. The two previous examples, both regressions are negative, and here we have, as we calculated before, r squared 1, 2 equal 0.75, and here we have r squared, sorry, it should be probably written somewhere here, r squared 1, 4, which is equal to 0.3. So here we have less dependence between independent variables, but also one of the dependent variables is independent variables is less correlated with the dependent variable. So we can see what is the result of the calculations here. Did we manage to increase the quality of prediction? And the answer is not, we didn't. The result is the following. x1 based on 2 and 4 reads 37.73 minus 0.82 x4 and minus 4.76 x2. So there are again completely different coefficients because there are different variables, and r squared in this case is equal to 0.79. So we really did take two variables that are much less correlated than before. However, because one of those variables was not correlated enough with independent variable, we overall got the quality of prediction which is even less than that was before. Before we managed to have it equal to 0.83. Okay, so here we can say that the differences in fuel consumption between cars with different number of cylinders and different weight account for 83% of the variability of the fuel consumption, and the differences between cars with different number of carburetors and different weight account for 79% of the whole variability of the fuel consumption. The last thing I would like us to do during this short lecture about the example is to derive the formula. So I will copy this formula somewhere, say, on the clear piece of a blackboard. we should also remember that what we can work with is, oh no, it's not right, it should be thinner. We work with the matrix of covariances. So there is C11, C12, C13, C21, C22, C23, and C31, C32, C33. So for 3 variables, one of them dependent, 2 of them independent, we want to derive the formula for squared correlation coefficient depending on the pairwise correlation coefficients. So let us look at the definition. These are 1, 2, 3 squared would be 1 minus the determinant of C divided by the variance of x1 variable, and C11, which is the algebraic complement of the element C11 indices down there of the full covariance matrix. I'm not really sure if in the previous recording, when I defined what is this R squared, and I said that okay, it is SST minus SSE, so total sum of squares minus error sum of squares divided by SST. I don't know if I did write this formula. If I didn't, I write it now. So this is the same formula but expressed with data coming from the total covariance matrix. This formula is general, so not only for number of variables equal to 3, but in general. Yeah, this is whenever we have the first variable being dependent variable, then this formula holds. And we will use now this formula in case of 3 variables, and we will try to derive this thing. So what we have to do is to make some calculations. So we start with the definition, R1, 2, 3 squared. The definition is written here. So first thing that we do is we write it on the common fraction. So there is the denominator, and in the numerator we have again C11, the variance of x1. The variance of x1 is C11 with indices with lower indices. So we will write it like that, C11. And I will also replace the variance here by C11. And now we will be working only on the data coming from the matrix here. Minus that C. What do we do then? We remind ourselves that if we want to calculate, say in orange, the determinant of C, we can use the Laplace formula, which is the following. We multiply this element by its linear complement, so the determinant of this matrix, then this element with the determinant of this matrix, and then this element by the determinant of this matrix. So using the concept of algebraic complement, this will be C11, C11 upper indices plus C12, C12 upper indices, and the same C13, C13 lower and upper indices. Therefore, for example, the thing that we have here can be written as say C11, C11 equals the determinant of C minus the whole sum which is written here. And we put the formula in our calculations. Then the determinant of C cancels, and we are left with minus C12 algebraic complement 1, 2 minus C13 algebraic complement 1, 3, and then divided by C11 algebraic complement of 1, 1. So now we use formulae for algebraic complements. We will definitely need to refer to our matrix, so I try to make it in such a way that, I know. I will take this, move it here, maybe a little bit rescale it. So this is our matrix. We can look at this matrix and we can write the formulae looking at the matrix. Okay, so we have in the numerator we have C12 and minus algebraic complement of 1, 2. Algebraic complement of 1, 2 with minus. It is the determinant of the matrix of not crossed elements. So there will be C21, C33 minus C23, C31. So that's this. Now this. There is minus C13, and I have to make this longer. An algebraic complement of 1, 3, which means the determinant of this matrix. C21, C22 minus, not C22, that's completely wrong, C32, C32 minus C22, C31. And then we do the same in the denominator, C11 times C22, C33 minus C23 squared, because this is the same as C32 and C23. It is a symmetric matrix, so this is exactly the same. Okay, so let us then multiply what we should multiply. Maybe I will move it a little bit higher, and then I can fit it on the same blackboard. So again, C12 and C21, this is the same. So there is C12 squared, C33, plus C12, minus, not plus, sorry, minus C12, C23, C31, and then Again, C1, 3, C2, 1, C3, 2. Not 3, but C. As we can see, these are in fact the same. Therefore, instead of writing it like that, I will put 2 in front of this. And then we have plus C1, 3 squared, C2, 2. So this is the numerator. And in the denominator, we have C1, 1, C2, 2, C3, 3 minus C2, 3 squared, C1, 1. So what we do next, we divide a numerator and denominator by multiplication of the 3 variances, which are here. So I divide this by C1, 1, C2, 2, C3, 3. And also here by C1, 1, C2, 2, C3, 3. And we look what happens. In the first case, C3, 3 cancels. And we are left with C1, 2 squares and C1, 1, C2, 2. Which are variances. This component is very similar. C2, 2 is cancelled. And we have C1, 3 squared divided by C1, 1, C3, 3. And then there is the minus of all 3 in the denominator. So this is the C1, 2, C2, 3, C3, 1 divided by all the variances C1, 1, C2, 2, C3, 3. Okay, and in the denominator we have 1 minus C1, 1 cancels, and we get C2, 3 squared divided by C2, C2, 2, C3, 3. Okay, so to understand this formula, let us first look at these summands. They are all of the form the covariance of variable xi, xj divided by variance of xi, variance of xj. So this is what we decided to call r squared ij. Therefore, we have, we can continue the calculations. We have r1, 2 squared plus r1, 3 squared minus something, and in the denominator 1 minus r2, 3 squared. And there is also a place here for this thing. We should remember squared, somewhere is squared here. We should remember that small r's, Pearson correlation coefficients, r, I, j, they are calculated with use of the unsquared covariance, and instead of variances we have standard deviations in the denominator. Therefore, if I multiply 3 covariances together, this is almost as multiplying 3 Pearson correlation coefficients together. then for each Pearson correlation coefficient, I have a pair of standard deviations. However, the same standard deviation will come from this component and this component, and these two standard deviations will arrange themselves as a variance, so they can be squared. Therefore, really, we have here minus 2 r 1, 2, r 2, 3, r 3, 1. So this is just the derivation. I mean, we got what we wanted. We can compare. Can we? No, because it doesn't fit to the same blackboard. However, this thing and this thing definitely look the same. However, we have to take into account the fact that such a simple formula of determining the multiple regression correlation coefficient using pairwise correlation coefficients is possible in 3 dimensions. So we have 1 independent variable and 2 dependent variables, and it is not that easy if we have more variables. Of course, it is always no, it is not always possible. No, I'm wrong. It is always possible using only pairwise coefficients inductively, but the formula will be probably very complicated and not really useful and readable. This formula is more or less readable. For example, this fact that if you take two completely uncorrelated variables as independent variables, then you just add the information that comes from those two variables. So this is something that we would like to have, such a situation. However, if it is not possible, then you may think, okay, it is good to have not correlated variables up to a point, because what you can see here is that this even small correlation is also subtracted from the denominator. So this dependence is not that completely clear. Okay, so that's all for now. This was the second pre-recorded lecture about multiple regression. This time we discussed an example, and we discussed this quite useful formula. Next lecture will be about partial correlation coefficients.